electrifying transportation. Electrifying the transportation is a promising approach. So the adaptation of electric vehicles into market has introduced very significant impacts on various fields, especially the power grid. The continued development of electric vehicle powertrain, battery, charger technologies have further improved electric vehicle technologies for a wider uptake. The current development of electric vehicles, bidirectional energy transfer to vehicle to grid, and their expected penetration in the IoE introduces a promising feasibility to exchange energy between vehicle and grid. And to give a brief history on electric vehicles, so the beginning of electric powered vehicle was favored because of the invention of the electric motor. In between the years 1832 and 1839, the first prototype electric powered carriage, which was powered by non-rechargeable primary cells, was invented by Robert Anderson. So the technology advancement of DC electric motor and rechargeable battery provided a major boost to EV industry. For instance, in New York City, the first commercial EV was introduced into the market, and it was an electric taxi in 1897. And in 1908, gasoline-powered vehicles such as Ford Model T were introduced, and it was introduced by Henry Ford. And in 1912, the invention of electric starter, by Charles Kettering, it removed the need of hand crank to start the gasoline-powered vehicles. But with all these, uh, due to several reasons, the EVs faded away and disappeared at the end of 1935. And after a few decades later, the government started implementing vehicles because of their advantages. In 1996, the first company, General Motors, produced and released the EV1 model. The next year, Toyota introduced the first world's commercial hybrid electric vehicle in Japan. And from 2010 onwards, all these battery electric vehicles, plug-in electric vehicles, such as Nissan Leaf, Mitsubishi, Chevrolet, and they have started to enter into this automotive industry. And to talk about some facts and concerns about EVs, what are the facts and concerns about it? They have to worry about the charging duration, where to charge, and the availability of charging stations, and we are using air conditioners, stereo, warmer, and they have to consider all these, and production and recycling of lithium-ion batteries. And we have to think, can this existing power station capacity and grid can handle this? Okay? We have such a grid and power generation capacity to handle only the needs of the people and industry. So if this EV comes into market to 100%, what will be the role of smart grid? How the grids are going to handle this? And whether this will create more peak loads and power quality degradation. And this is one concern. And we have to consider about the cost of building fast charging stations at house, and how to determine EV charging within a shared apartment, annual degradation of battery, and switching from oil to coal, and we have to consider the economy also. So these are the facts and concerns about EVs. So just to tell a few words about the overview of EVs, they are different from conventional vehicles because they use electric motors for propulsion, while the later utilize an IC combustion engine. In recent years, much attention from industry and academia has been drawn to EVs with plug-in feature. Specifically, two types of plug-in electric vehicles are studied: battery electric vehicles and plug-in hybrid electric vehicles. So, let us say about all electric vehicles. So, the typical architecture of this Plug-in electric vehicle. It is composed of three major parts, namely electric motor, rechargeable battery, and the controller. The electric motor utilizes rechargeable battery as the energy source to generate propulsion. The two-quadrant controller is only capable of managing the power supplied to the electric motor, which drives no vehicle to move forward or backward, while a controller which can also support regenerative braking is known as a four-quadrant controller. So this is the all-electric vehicle. So here we have the rechargeable battery. And, the next one is plug-in hybrid electric vehicle. So, so it is classified on the basis of the different types of powertrains. Hybrid it is classified into three categories: parallel hybrid, series hybrid, and power split hybrid. So among these, uh, commonly used is parallel hybrid. Parallel hybrid electric vehicles are usually equipped with both an electric motor and an additional IC for propulsion. This mixed propulsion system enables the PHEVs to be driven in two modes. One is charge depleting mode and the charge sustaining mode. So when operated in CD mode, this mainly draws energy from onboard battery pack. If the battery state of charge has been depleted to a predetermined level, this will switch to CS mode and utilize IC system for further propulsion. And coming to the timeline of EV technology evolution, the first one is mode selector, followed by electric motor, ultra capacitor, battery bank, fuel processor, power split, parallel hybrid electric vehicles, complex hybrid electric vehicles, then fuel cell vehicles, then series parallel hybrid electric vehicles, then series hybrid electric vehicles. And coming to the EV charging scheme, so the charger type, charging level, and charging topology of EVs have significant effect on the grid because charge scheduling and battery management can affect the performance of the grid. So EV battery performance, including safety and durability, is highly dependent on the charging method and time. Uncontrolled charging creates negative consequences in the battery performance of the grid. Currently, the battery has its onboard battery management system. The fast charging station also needs some sort of battery health management system to improve both battery and power grid health. So, some of the charging methods of EVs are constant current charging. So, here constant current is maintained in the scheme by controlling the voltage of the battery or cell. And the next one is constant voltage scheme. This is the very simplest and most common charging method in which the battery charges at a constant voltage during the charging period. Charging the current varies over time. The battery SOC is at a minimum level and current is high at the initial stage. However, over the time, the charging current goes to its minimum level as the SOC reaches its maximum level. Using this method, EV draws a high amount of current and it is unavailable in most distances and parking situations. The next one is constant current and constant voltage combination. So initially the battery will be charged slowly with constant current method and the later voltage is kept constant and the current increases. So a threshold value will be set and if the SOC reaches that value, the charging is switched to constant voltage. Then these are the battery capacity and technologies by various EV manufacturers. So Chevrolet, US Alpha, Lee, Tesla, Chevrolet, these are the capacities. And coming to the EV charging and electric grid interaction, there are several charging levels for EVs that reflect the power capability and charging duration. These levels have been standardized to reveal the EV slow or fast charging scenarios. The slow charging can be experienced at home or office, and it is a dedicated charging station in commercial or public places. The charging power delivered is usually determined by the nominal ratings of the battery charger, and in most recent studies, the EV battery voltage is typically limited to less or equal to 400 volts. And there is a great debate on how to standardize the first charging versus. However, fast charging is essential for charging the EV battery within few minutes. The recent developments of universal charging uh, by global automakers in collaboration with Society of Automotive Engineers (SAE). It incorporates both AC charging and DC fast charging solutions. It combines AC single phase charging, AC three-phase charging, and ultra fast DC charging in single unit connector. The AC DC charging level characteristics as given by Society of Automotive Engineers. These are the standards. So the first one is EV charging configuration at AC level 1 and level 2 setup. So in this figure, this figure, it is a setup of the facilities at the charging point. With AC level 1 and 2 configurations, the electric vehicle supply equipment is provided at the charging point by supplying the AC power to an onboard charger. And the next one is EV charging configuration at DC level 1 and 2 setup. So here, with DC level 1 and 2 configuration, the charging point supplies DC current to the EV battery pack. Then, what are the challenges in EV charging? So the acceptance of EVs is highly dependent on the driving range, flexibility, and refueling. Most of the factors are potentially related to the EV charging system. So the factors to be considered in EV charging are the expedite global acceptance. Equipment manufacturers should develop common standard components to use globally, but the devices and standards are not homogeneous across. The customer charging experience of EV is keep similar everywhere, like the fueling of an internal combustion electric vehicle. And a few infrastructures cannot be shared with others, which increases the cost. So the major challenges in EV charging can be listed as fast charging implementation, demand charges of fast charging, and charging station location. So fast charging implementation, it consists quick charging is the latest trend in the EV industry. A fast charging installation is expensive, which hinders its availability. If the lithium-ion battery is not overheated, then fast charging can change the battery to 80% within 15 minutes with three available systems: Tesla superchargers, combo, and CHA demo. Then demand charges of fast charging. Demand charges are a key barrier for fast charging development. Sometimes the charging station owns excess energy, but the owner has to pay a fixed monthly fee, and ultimately that additional charges goes to drivers. Then charging station location. EV charging station location is important to ensure its reliability, but in some cases it has been found that the location of the charging station is not an optimum location, which can increase the cost. And coming to the next challenge, it is a big challenge to charge EVs in a shared apartment and measure the energy consumption. And we have to concern about the utility. So for a widespread EV charging station, the utility needs to be upgraded and the line capacity, substations, transformers, etc. The main concern of the utility is to control the grid during peak charging and peak demand. For present, 50% of level 2 charges may share a transformer, therefore the utilities need to prepare for situations where multiple consumers will charge their EVs from the same transformer. And here some of the building issues for business purposes are not worked out properly, such as the building of third-party operated stations, smart building in public stations, and the tracking and billing of an EV owner charging stations in an apartment connected in a complex network. Sometimes sub-metering is used to ensure an incentive or determine specific energy usage in apartments. Then EVs with B2G system architecture. So electric vehicles can be integrated into power systems and operate with different objectives such as dynamic loads by drawing power from the grid, or dynamic energy buffer by feeding power to the electric grid, that is vehicle to grid. With the bidirectional infrastructure, the implementation of V2G concept will become feasible by controlling and managing the energy exchange between the power grid and EV battery. In V2G operation, the charge level of the EV battery is continuously monitored and allowed to be discharged to smart grid. The proper V2G management of a large fleet of EV are important for various benefits such as active power regulation, reactive power regulation, and also service support. Then coming to the potentialities of EV's integration into the future smart grid. So this chart explains the EV's integration into the future smart grid. So this I have explained now. So now energy management of Internet of Energy. So to ensure energy management system, a real-time MPM communication system is necessary to exchange information between energy devices, especially power generation and consumption forecasting, pricing, and device mobility. The infrastructure of the IOE will consist of an intelligent power infrastructure with a reliant communication network to control and monitor the system in real time. All the energy generators, consumers, and devices are connected with bidirectional energy and data flow systems. The customers are connected through peer-to-peer connection systems where each user can supply or consume power, being then known as prosumers. Consumer-owned energy devices like EV and storages can be integrated into the power system as a plug and play and can sell their excess energy to the grid. Coming to the infrastructure management, so infrastructure for demand side management. So here, so this EV charging management systems need to be part of the integrated demand side management and utility energy procurement and dispatch. So the charging of an EV along with other domestic loads should follow the local infrastructure management through coordination with the local transformer and then coordinate with the neighboring feeder to ensure grid reliability. Installation of advanced metering infrastructure will help the utility to distinguish EV charging energy from primary meter through a separate submeter and seamlessly bill EV charging at the present energy rate. So this advanced metering infrastructure installation will also help it to utilize and evaluate the energy usage due to EV charging, which can be used in greenhouse gas emission studies and also to predict the local power system reliability. Then coming to distribution management integration, the integration of electric vehicle supply equipment with the distribution management system will provide flexibility to the utilities to manage reliability electricity delivery and also to plan and expand the existing networks to accommodate EV demand. It will also help to ensure the quality of the power with the increasing number of renewable energy penetration. To support EVs and smart charging in smart grids, the following grid management measures are recommended. One is coordination with generation. So here the utilities can optimize the intermittent renewable generation and reduce the peak demand by managing the EV charging with the proper coordination between generation and EV charging. So demand response integration, which is normally called as DRI. By installing DR programs, the smart grid can control the charging of the EV according to the load conditions. In distributed intelligent devices, that is nothing but sensors and communication facility of the smart grid, can coordinate among the load, generation, and power networks to optimize EV charging. For example, a transformer integrated with intelligent systems can communicate with the EVAC to control the charging frequency of an EV to avoid being overloaded. Then the market-related services. In this, the future grid should have the provision to accommodate all types of generation systems that customers can provide service back to the grid. The grid should also have the provision to offer optional services like DER support and microgrid services and should facilitate a retail market for consumers and third-party providers to buy and sell the services. Then virtual power plant realization and control in B2G context. The conceptual framework of the VPP offers an aggregation scenario that uses control and information exchange between the utility entity and the EV fleet to facilitate the V2G realization. The control approach in the VPP can be centralized or it can also be distributed. In centralized control scheme, the decision making and the data exchange are based on the PPP Central Control Center, which is called as BPTC, while in the distributed control scheme, the decisions and flow of information are fully achieved in the distributed manner. On the other hand, the scheme includes some decision making and information exchange levels within the spatial VPP model. So within the electric grid and energy market players, the EV aggregator will operate as a virtual power plant. The clustered EV fleet at charging station provides status like available SOC that communicates with the aggregator control center. This local VPP control. So this diagram shows that. So coming to the bidirectional energy transfer of electric vehicles. So bidirectional energy transactions of this electric vehicles. It is a crucial feature of the Internet of Energy. So this IOE facilitates the plug and play features helping to integrate energy devices to the system. So it will allow distributed RES, EVs and energy storages to automatically connect to the grid and contribute to the customer's demand without any modification to the system. The use of energy router facilitates the integration of devices at different levels and types. It is an advanced version of the traditional transformer having information processing and voltage level conversion capability to dispatch electricity to consumers smartly. When any new V2G is connected to the system, the energy router checks the load power demand and based on that it grants request to the V2G to generate power. At the domestic point, advanced metering unit, battery management unit and EV charge management unit will coordinate with the main domestic EMS unit to economically charge discharge storages. While comparing this unidirectional V2G with bidirectional V2G, so unidirectional V2G technology controls the EV charging rate in a single power flow direction from the grid to EV board on energy rescheduling and incentive systems. But in bidirectional V2G, it refers to the dual direction power flow between EV and the power grid to achieve maximum benefits. And coming to the application of RES with EV in various power systems. So the solar photovoltaic and this EV. It can be used in smart houses, parking, grid distribution networks, microgrid, and the EV's interaction with the microgrid. The microgrid, which is composed of wind power, PV solar power, distributed energy generators, and battery swapping stations. When this electricity generated by RES is surplus, EV batteries and BSS will be charged. The power demand is in shortage, EV batteries and BSS can discharge as electricity source. The basic idea is to schedule the aggregate of EVs, BSS and loads to maximize the operational cost to microgrid. So now coming to the concept of EVs intelligent integrated stations and its energy flow. So because of the issues like air pollution and global warming, and also considering the fossil energy reserves and energy prices, electric vehicles now are gaining increasing attention to reduce dependency on fossil fuels as well as environmental pollution. However, such issues like higher costs, short driving range, and long charging times, they are the constraints for EV development. The smart operation is considering intelligent charging, discharging of EVs in distributed networks and load environments to reduce both cost and emissions simultaneously vary in sectors. performance of EVs is influenced by the energy capacity of the onboard energy storage system, which is called as battery pack. Several factors, several factors such as deep depth of discharge, high or low temperature, extreme state of charge, are usually acknowledged to accelerate capacity fade. In addition, many studies focus on the charging scheduling of EVs as a charging station. So, in recent years, V2G technology has drawn attention of the researchers to improve the performance of electric grids in terms of efficiency, stability, and reliability. This V2G facilitates a large pool of EV batteries to store the energy during off-peak hours and inject it back to the grid during the peak hours, thus achieving balancing and peak shaving. The increasing number of electric vehicles connected to existing distribution networks at time variant loads for significant distortions in line current and voltage. So the EV's intelligent integration systems making full use of retired batteries is to offer a potential solution for accommodating the charging demand of EVs. So it proposes the concept of generalized energy in IAS based on the energy flow between IAS and EVs and in between IAS and the power grid to systematically evaluate the energy capacity of IAS. So now coming to the intelligent integrated stations. So most operation models in the field of EV charging stations are decentralized and by constrained by the factors such as shortage of plant area, the high price of batteries, and restrictive integration standards of the power grid. The most research on charging stations focuses on avoiding charging during critical peak periods to prevent the failure of the grid due to over-demand. Therefore, the development of EV charging stations is considered by cost and service quality. An IIS is an electric system cluster composed of a charge exchange system, a battery system, multi-purpose converter devices, and a dispatching center as shown in this figure. So the energy flow will be like this. The dispatching center collects information inside and outside the IAS and coordinates the power exchanging processes considering the operation state of the power grid, EV's battery charging request, and energy capacity of IAS. The EV terminal installed in a vehicle is able to record the position of the vehicle and exchange information with the dispatching center based on GPS technology. The dispatching center plays a fundamental role in battery management. It is capable of predicting battery exchanging requests based on information from the EV terminal. So the information about the vehicle location is important for calculating the SOC of EV battery. The EV battery energy consumption is proportional to its driving distance. So we can calculate the battery SOC according to its initial energy capacity, location, information, and the driving speed. Based on the information about EV's battery SOC, we can estimate the EV's battery exchanging request and check the number of available full capacity batteries in IAS. And in order to coordinate battery exchanging request of EVs and interact with the power grid, the availability of information flow plays an important role in the battery management and operation of the IAS. The term information flow in the IAS it covers many parameters like SOC of batteries, which indicates energy capacity of batteries in the CES and EVs, operating parameters of converters, which indicate the information of power flow between IAS and the power grid, the information of EVs, onboard batteries through GPS technology, information of the power grid through energy management system. It's called as EMS of the grid. So here the Internet of Things is also a natural extension of supervisory control and data acquisition, which is called as SCADA. It is a category of software application, programs for process control, the gathering of data in real time from remote locations to control equipment and conditions So these SCADA systems include hardware and software components. The hardware gathers and feeds data into computers, such as SCADA software installed, where it is then processed and presented in a timely manner. The evolution of SCADA is such that the late generation SCADA systems developed into first generation IoT. To intelligent dispatch control to realize the fusion of multi-source information from the grid, EVs and IAEs, a dispatch platform is needed to cooperate with EMS and the supervisory control and data acquisition systems. The data collector in the dispatch platform is in charge of collecting operating information on the IAEs and EVs for the operator workstation. So the operator workstation also collects the grid operating information through the SCADA and EMS via the communication server. So this IAS includes a web server which is able to obtain and upload information to internet, an EMS server which is used to detect the load level of the grid and form smart dispatching strategies based on the grid operating information. The SCADA server is employed to acquire the scene information and send the decision-making information to corresponding systems, and the data store server which stores a large number of data during the operation of IAS, which is of great value for establishing and dispatching strategy by analyzing and forecasting the changing trends. For example, by monitoring the information about EVs in operation, we can analyze the forecast batteries, exchanging requests, and send this message to the system. The dispatching center will be able to collect all kinds of information such as location and operating status of EVs, the energy capacity, the charging discharging power of CES, the dispatching order, and the operating status of the grid, and the information on power flow in each converter. The basic charging discharging strategy aims to satisfy EV's batteries charging requests and optimize charging processes of this IAS to achieve peak load shifting. Into the control strategy to power energy flow in IAS. So according to the operating status of the grid and energy capacity of IAS, we can provide auxiliary services to the power grid such as frequency control and reactive power control by controlling the power flow between the power grid and IAS, called a smart value adding strategy. The frequency control strategy is applied to IAS when the deviation of frequency del F is in a setting range. So if del F is greater than 0, then this IAS charges from grid in rated power. Otherwise, IAS does not charge from the grid or even discharge to the grid. Moreover, this IAS can operate as a static bus and generator to compensate reactive power for the distribution grid. Then coming to the charge exchange system. So this is the layout of the charge exchange system. So to satisfy the EV batteries charging demand, the CES can provide fast charging and slow charging services. Moreover, the CES is expected to provide full capacity batteries for EVs in the batteries exchanging mode. Therefore, EV batteries can be replaced in a short time, and the batteries in the CES can be charged during off-peak periods. The CES consists of EV batteries, exchanging room and charging room, control room, and maintenance center, which is shown here. So this EV batteries charging room provides batteries exchanging, fast charging, and slow charging services for EVs. The control room is in charge of monitoring and controlling the operation of this EVs. The maintenance room provides charging, maintenance, and storage services for batteries in CES. Therefore, the CES is supposed to provide maintenance service for batteries as well as the batteries exchanging charging services, aiming to overcome the significant exchanging demand of batteries caused by a large level of EV penetration. Internet of Things and GPS technologies are used to monitor EV's operation in order to obtain batteries exchanging forecast information. And coming to the battery management in IAS. So this battery management in IAS is associated with IoT system and collects information on batteries inside and outside. So IAS to provide good services for drivers and send dispatching orders to corresponding systems. So GPS technology is used to monitor EV locations and collect driving information. IoT needs to estimate the SOC of EV onboard batteries according to their driving information. Based on the energy capacity, based on the energy capacity of EVs, IoT will provide additional important additional important services such as diagnosing EVs operating states and sending messages to the maintenance center so when any EV is in trouble. Moreover, IoT is able to obtain information from CES, EBS, such as energy capacity of CES and the operating state of each battery. So by detecting the status of batteries in CES, IoT gives dispatching orders such as sending retired batteries to EBS and transporting faulty batteries to the maintenance center. So, so with this battery management in IAS, it could be connected and autonomous electric vehicles. So this connected and autonomous electric vehicle concept, which is shortly called as CAEV, they are the complex automotive systems combining connected vehicles, autonomous vehicles, and electric vehicles. So a connected vehicle is a vehicle with technology that enables it to communicate with nearby vehicles, infrastructure as well as objects, but may not be automated nor electrically operated. So while an AV, autonomous vehicle, is a vehicle that is, in the broader sense, we can say that it is capable of driving itself without human intervention. An EV is a vehicle that powers up and operates with energy stored in the battery. So typically, a connected and autonomous electric vehicle, that is CAEV, it is a vehicle that is not only capable of sensing its environment and navigating with little or no human input and communicating with other entities, but also it is operated by the electric power. So this may collect various sensor data through intra-vehicle communication systems and feed the data to in-vehicle applications. The connected vehicles refer to the wireless connectivity, enable vehicles that are communicate that can communicate with their internal and external environments, that is supporting interactions of vehicle to sensor on board, that is V2S, vehicle to vehicle, V2V, vehicle to road infrastructure, V2R, and vehicle to internet, V2I. The number of sensors is forecasted to reach as many as 200 per vehicle by 2020. Such a big quantity of sensing elements are required to report event-driven or time-driven messages to the electrical control unit. So now coming to the IoT technology and this CAEV. The IoT enables information exchange between CAEV, its surroundings, and the smart city. So using onboard IoT devices, data from ECU, that is electronic control unit, such as speed, temperature, location data, and other sensor data can be obtained for the vehicle. Whereas with IoT devices, environmental and traffic information can be provided to the vehicle. The IoT enables situation awareness services such as sharing and processing image and video information, detecting critical situations and alerting CAEV, enabling object detection on the road and obstacle avoidance, furnishing information on accident ahead, and provisioning road conditions. So, IoT-enabled driving allows the vehicle to identify traffic signs, markers, and signals and respond automatically. So there are five major components of CAEV. So one is perception system, second one is localization and mapping system, third one is driving policy system, fourth one is communication system, and fifth one is storage battery system. So this perception system is responsible for sensing the environment to understand its surroundings. And this localization and mapping system enables the vehicle to know its current location. So this driving policy system, it is referred to the decision making capability of this CAEV. under various situations. Communication system, it is connected to the surrounding environment such as vehicle to vehicle, or vehicle to infrastructure, or vehicle to anything. Then storage battery system. This system includes charger and battery packs in the vehicle. So SOC level determines the amount of charge stored in the battery. And this vehicle automation can be basically classified into different levels, ranging from level 0 to level 5, corresponding its full automation. For example, automated driver resistance systems such as adaptive cruise control correspond to lower automation level, while fully automated driverless vehicles correspond to higher automation level. So the Society of Automotive Engineers define levels of vehicles, different levels. So level 0 to level 5. Level 0 is no automation. Level 1 is driver assistance. Level 2 is partial automation. Level 3 is conditional automation. Level 4 is high automation. And level 5 is fully automation. So this level 0, this is no automation. So the human driver is responsible for everything and for all the driving tasks, including control of the car as well as monitoring the road and the environment around the car. Level 1 is driver assistance. So in this level, the human driver is assisted by either steering or acceleration by the driver assistance system, but not both. For instance, for example, we can say adaptive cruise control. And level 2 is partial automation. So here the driver assistance system takes care of both acceleration as well as the steering of the car. So while the human driver monitors the road and environment around the car. And level 3 is nothing but conditional automation. So in this level, the automated driving system undertakes all aspects of the dynamic driving task with the expectation that the human driver will respond appropriately to a request to intervene. So thus it requires partial supervision of the driver. And level 4 is high automation. In this level, the automated driving system undertakes all aspects of the dynamic driving task, even if a human driver does not respond appropriately to a request or intervene. So this level is basically unsupervised. So the last one is fully automation. So in this level, the automated driving system undertakes all aspects of the dynamic driving task in all roadway and environmental conditions. So this level does not require driver at all. So coming to the overview of IoT and autonomous stack for the IoT AV platform. So in recent years, now we were talking about Internet of Vehicles. So, so the CAV is connected and autonomous vehicle. So CAEV is connected and autonomous electric vehicle. So while talking about Internet of Vehicles, so we have to talk about Internet of Connected and Autonomous Vehicles. So now in recent years, many government agencies they are actively involved in this type of research for the development of IoT technology and mainly this IoTAV. So this IoTAV can be seen in two different tabs. One is IoT stack and autonomous driving stack. So the vehicle uses own intelligent sensors to collect raw data from the vehicle to diagnose and analyze the data record the driving information and resolve the task. It also exchanges data with other entities in the vicinity such as roadside units, vehicles, traffic lights. So this IoT platform acts as a collection center for large amount of data from various connected IoT devices. Using this IoT, it provides supplementary source of data for the vehicle and enables efficient and robust applications and services. This IoT creates an integrated platform for supporting numerous services such as intelligent traffic management, intelligent vehicle control, and dynamic information services. So the major components of this IoT are vehicle IoT integration, IoT platforms and architecture, and communication network. This vehicle IoT integration enables using IoT devices in vehicle sensors for various functions such as local dynamic mapping and provisioning autonomous driving functions and data fusion functionality, as well as includes vehicle IoT enabled platform and communication modules. So this IoT platforms and architecture may include various IoT enabled CAVs such as car sharing, platooning, taxi, automated parking, automated charging, etc. So this communication network is a network layer that allows the exchange of information among vehicles, RSUs, pedestrians, sensors and actuators, and cloud infrastructure using communication protocols and standards such as Wi-Fi, Bluetooth, 3G, 4G, then LTE, long-term evolution, 5G, and etc. So this CAEV charging management system, it includes various actions such as charging station operator, network provider, utilities and IoT platform, etc. So it is based on the C-Charge platform, C-Charge CAV server, wireless charging station operators, and energy service providers. So these ESPs are autonomous entities producing and distributing energy to the consumers. These consumers may be private or public. So whereas this this is fundamentally accountable for operation and maintenance of wireless charging stations. So typically they can manage multiple WCS at various charging locations. So a C-charge system, which is a central component of the system architecture, acts as a smart management center for EV charging. It is designed for facilitating charging services to the CAVs by providing effectual coordination with various EV charging networks. On the other hand, this charge server may provide charging related to services including finding WCS location, assigning reservation, and managing CAED information and financial transactions. So on the also, C-Charge server is responsible for interacting with the WCS host for efficient smart charging. This exchange system may establish agreements with different WCS hosts in the EV network, such as they can charge in the entire EV charging infrastructure. So this CAEVs can also be used for taxi services. So one of the appealing use is CAEV taxi service. The main objective is to provide ride hailing using CAEV. It can be observed that a fleet of moving CAEVs around the urban city might drastically change land usage, for instance, reducing the parking area required in the urban environment. The main advantage of this connected and autonomous electric vehicles, the main advantage of this connected and autonomous electric vehicles are improved safety, greater mobility, increased car sharing, increased road capacity, fewer CO2 emissions and pollutants. So it offers many potential advantages in terms of sustainable development for environment-friendly urban mobility. Uh, while talking about this improved safety, it may eliminate many of the accidents caused by human error, estimated at about 90% of all accidents. And it gives greater mobility by providing services to those who cannot drive, including elderly, disabled, and children. And it may significantly reduce the need for individually owned cars. So it increases car sharing and it increases the road capacity through fleet platooning, more predictable traffic flow, and reduced congestion may be achieved. And using the electric power to operate, it may reduce GHG emissions as well as air pollution, minimize environmental impact, improve quality of life in urban area due to fewer CO2 emissions and pollutants. Then coming to this IoT-based EV charging system. So, using this IoT based EV charging system, it is expected to maximize the adoption of EVs to facilitate users' range anxiety. Therefore, connectivity between the charging station is mandatory. Understanding the real-time status of the charging systems can provide valuable information to users such as availability of charging provisions and time to reach the charging stations. IoT paradigm offers the present facilities a real interactional view of the physical world by a variety of sensors and broadcasting tools. The real-time server-based forecasting application is necessary to provide scheduling management, to avoid waiting time, and to provide a real-time CS recommendation for EVs in economic cost and reduce charging time. In addition, the development of such application avoids third-party intervention and protects EV users. Uh, It gives privacy and complex information exchange system between the users and the end users can easily use the CS between uh, any requirements. Then EV load forecasting and SOC measurement. The load forecasting of EVs at CS is an important process that can increase the efficiency of the distribution network, and it is accurate prediction has a huge impact on the operational efficiency. So generally, a user may prefer a station where there is availability nearby. Obviously, intimating the accessibility of slots during a precise time will avoid congestion significantly throughout peak hours at the users. So insufficient number of CEOs will lead to complication in load forecasting as well as in energy distribution for the EV users. The energy distribution crisis may affect the EV user, and to overcome this problem, a better battery management system is needed. So, to for experimental validation of the IoT-based SOC system, uh, they have created an algorithm. So the first, the step-by-step algorithm to initialize the coolant counter and Arduino, assign the voltage as zero, make communication between system and Arduino, connect the load with the battery and run it. Coolant counter will feed the results to Arduino, convert and store the result from analog to digital format, and then display the result. So when the battery reaches a safe SOC, notify to the user through a message. If the battery is plugged in for charging, the coolant counter goes to the ideal state until completion of charging, or if not plugged in, it will continuously send alert messages up to fully discharging of battery, and it will terminate the connection. After charging of battery, the coolant counter changes the state from ideal to running state. If an EV user arrives at the book CS earlier, he will use reserve points allowed by the CS for EV users with no booking or yearly arrival. So these reserve points help to support the CS by first charges in case of emergency and abnormalities. So arrival time-based priority algorithm will be used in such cases. So this ATP algorithm allows the vehicles into service once they arrive and hence reduces the delay time and avoids charger to be idle. So the Android-based application can be developed to receive the updated available slots from the CS and location of EVs with an interval of 1 minute. Once the SOC of the battery reaches a specified limit, the EV users will take the decision to charge. So this is application developed application. The user has options for their total battery capacity, location, and available SOC. The user has to fill the battery capacity of the vehicle. The location of the SOC of the EV can be identified either automatically with Arduino and GPS or else manually. So considering an EV such as Mitsubishi, uh, which is traveling from Pondicherry to which is traveling to Pondicherry from Chennai, it will have reached the safe SOC when crossing Poteri. Therefore, the user has to recharge the vehicle's battery. The user can travel up to a maximum distance of 22.5 kilometers at average speed. The status of the nearer CS can be obtained from the application based on the inputs taken from the GPS tracking system. It shows the relevant information to the CS such as the name of the service provider, distance from the present location, reachability, total number of charging slots engaged and available slots for charging, electricity price per kilowatt hour, availability of fast charging option, and the optimization score. So based on the remaining battery capacity, the application will indicate whether the CAs are within the range or not. So such a robust application is beneficial not only to EV users but also to the CES to predict the future load, to avoid congestion, and for energy consumption reduction, and also load balancing. So here, in this regard, the paradigm of IoT is increasingly integrated with real-world applications, particularly in the energy sector. So to conclude, the range, energy density, and capacity of the electric vehicles battery are expected to increase in the next decade. The EV technology is expected to evolve rapidly along with its charging schemes and related infrastructure. So in the future, uh, grid connected, um, the coordination between the power systems and the communication systems will make the power system fully automated with advanced energy management systems. So therefore, technological EV advancement, the adaptive charging infrastructure, and coordination using reliable communication systems, and reliability available tools to quantify the impact on power grids are essential to ensure the maximum benefits for EV with distribution generators. Thank you. I thank the organizers of this ACT sponsored SPTP for giving me this opportunity to uh, give about the basics of intelligent management of electric vehicles within IoT. Thank you, Mr. Ravindran.
Thank you. And thank you, ma'am. Thank you for presenting and giving a wonderful topic presentation. And I have shared a feedback link. Is it okay? I think it's for registration. Okay, sir. I will just give you, sir, 1 second. I will give you a right link for the feedback. Feedback link. Sir, now I have given a link here, sir, for feedback, and you can try this now. And I hope session is very useful to you all. And I take this opportunity to thank our department management and our resource person for giving a wonderful session over this topic. And I take this opportunity to thank everyone for your kind observation on these topics and your passions. Uh, Happy learning. Thank you. And you can fill the feedback form. Thank you.